Okay, so 2.58 introduces not monovalent metals, which are basically metals in which there's one free electron per atom that basically just roams around throughout the object. If you know about sort of electron seas and that kind of concept, that's basically what a monovalent metal is, with the difference being that there's an added specification that each atom gives exactly one electron. So the question is, why does this material actually form, and why it doesn't just fall apart into a pile of individual atoms? And the answer to that is sort of the fundamental concept behind everything, why everything happens, which is that the universe is constantly trying to enter a state of minimal energy. So any process that lowers the energy of a given system is going to be possible to occur for a given system. So in this case, we are going to treat the atoms as basically just infinite square wells, with the electron being the particle in the middle. And we basically want to show that the arrangement of a bunch of separate atoms has a higher energy value compared to if we had all of them combined together. So we're going to start with part A, which is going to be an estimate of the energy of a bunch of isolated atoms. And what we're going to do is we're going to treat each atom as an infinite square well, and that free electron as just a free particle inside that infinite square well, and we're going to estimate this energy. So we have this nice little picture to sort of go with it. And we already know what the ground state energy of an electron in an isolated well is, and we're told to assume that the electron is in the ground state. So we know that for an infinite well, the energy values are equal to n squared, pi squared, h bar squared over 2ma squared. So if every electron is going to be in the ground state, then every electron is going to have an energy of pi squared h bar squared over 2ma squared, because n is now equal to 1. And given that we have n atoms, which are isolated from each other, the total energy is just summing this n times, or the total energy is just n times E1, which is going to be equal to n pi squared h bar squared over 2ma squared. And that is part A. Okay, next, part B, is we're now going to do the same thing, but instead of treating them as isolated atoms, we're going to treat them as a collective by considering this as a set of n free particles in an infinite square well of length Na. So, we are given this extra thing, which is the Pauli exclusion principle, which is basically this idea that there can only be one electron per each allowed state, two if you include spin, but for now we're going to ignore spin. And we're going to say, what is the lowest energy for the system? So exclusion means that every single electron occupies a single given energy state in this infinite square well. So as a result of that, the total summation for the net energy is going to look something like this. So once again, we have sort of the energy levels for individual electrons in this square well, which is going to be n squared, pi squared, h bar squared over 2 times the mass of an electron, and this time instead of a squared is going to be Na squared, because that's the length of our well. So each individual electron in this well is going to have an energy value like this. As we add more, the energy is just sum. So if each electron can only take on one energy level, the total energy level is going to equal. So we have an electron in the first state, which is going to be pi squared h bar squared over 2m Na squared, and then we have our second electron, which is going to be in the n equals 2 state, 2 squared pi squared h bar squared over 2m times Na squared. And then our third electron, which is going to be in the third state, 3 squared pi squared h bar squared over 2m times Na squared, plus and so on and so on and so on and so on, all the way to n squared pi squared h bar squared over 2m times Na squared. And we can rewrite this as a summation, moving all the constant out. This will give us pi squared h bar squared over 2m Na squared times the summation from n equals 1 all the way to n equals capital N of n squared. So this summation term is called a sum of squares. This is a very common summation term, and it actually has a formula to it. We can rewrite it effectively as n times n plus 1 times 2n plus 1 divided by 6. And there's plenty of derivations online that go over how this works. I'm not going to bother with it because it's a little bit of a tedious one, and I don't really want to go through it right now, considering that that's more of a math territory than physics. So just know that this summation simplifies down to this formula. If you want to know how to do it, just search up a derivation online. But if we do that, then what we're going to get, or sorry, my apologies, I did the indexes wrong. This is supposed to be capital N's, because we're summing up to capital N. So if we do this, then our total energy is going to become pi squared h bar squared over, and I'm now going to multiply over, so 2m n squared a squared, multiplied by, and this is, let's see, what's this going to give us? N times 2n squared. Well, actually for now, I'm not going to multiply this out. I'm just going to leave it as is, because we're going to multiply this out in part C. So multiplied by n times n plus 1 times 2n plus 1 divided by 6. And just so we can collect some terms, we can do some cancelization here. So the big N cancels out with one of the n squareds. This gives us pi squared h bar squared over 2m a squared times n plus 1 times 2n plus 1 divided by 6n. And that is the energy of our combined system. Okay, so in part C, we're asked to find a cohesive energy, which is just the difference between these two energies we found in part A and part B. So the cohesive energy is going to equal N times E1, which is arguably our larger energy, which is the isolated set, subtracted by the E that we calculated in part B, which is our combined set. So this is going to give us N pi squared h bar squared over 2m a squared minus pi squared h bar squared over 2m a squared multiplied by n plus 1 times 2n plus 1 divided by 6n. So at this point we can combine some terms, use the distributive property, get the pi squared h bar squared over 2m a squared out. This leaves us with n subtracted by, and let's expand this out fully, 2n squared plus n plus 2n plus 1 divided by 6n. If I combine this, this gives us pi squared h bar squared over 2m a squared multiplied by 6n squared minus 2n squared plus 3n plus 1, all divided by 6n. Simplify a little bit more. This leaves us with pi squared h bar squared over 2m a squared multiplied by 4n squared. And I feel like I made a bit of a mistake right here. Yes, I forgot to switch the signs when I'm subtracting over. So this should be minus and this should be minus. My apologies. Okay, so 4n squared minus 3n minus 1 divided by 6n. Okay, now we're told to find cohesive energy per atom in the limit of large N. So let's start by finding the cohesive energy per atom. So in that case, we just divide CE by N, because remember there's N total atoms. So this is the cohesive energy for all N atoms. So the cohesive energy per atom is going to be CE divided by N, which is going to be pi squared h bar squared over 2m a squared multiplied by 4n squared minus 3n minus 1 divided by 6n squared. And now we want to find the limit as n goes to infinity, because we want to take the limit of large N. So the limit as n goes to infinity of this expression, CE over n, is going to equal pi squared h bar squared over 2m a squared. And then over here we have, you know, the n squared term being the largest factor. So this cancels, or sort of the n squared makes the 3n and 1 negligible. And as a result, we just have 4n squared over 6n squared, or 4 over 6 as a common limit problem. This simplifies down to 2 over 3, so we're left with 2 pi squared, let's see, no. The 2 cancels out with the 2, this cancels out with a 3, so we're left with pi squared h bar squared over 3m a squared. And that is our cohesive energy in the limit of a very large value for n per particle. Okay, finally in part D, we're just plugging everything in. We're going to say that A is roughly equal to 4 angstrom. So if we plug everything in, then we have pi is going to be equal to 3.14. The mass of an electron is about 9.11 times 10 to the negative 31st kilograms. H bar is equal to around 1.05 times 10 to the negative 34th joules times seconds. And then what other variable? And then we have angstroms. So A is equal to 4 angstroms, which is 4 times 10 to the negative 10th meters. So if we plug everything in and into sort of pi squared h bar squared over 3 ma squared, what this should give you is a value that's roughly around the range of 1.56 electron volts. So that is smaller than what we expect. However, keep in mind that way up here, we ignored the factor of spin. So if we include spin, then 2 electrons can fit in each energy state for this infinite square well. So realistically, this would be it would be pi squared h bar squared over 2m times na squared plus a second term that's also pi squared h bar squared over 2m times na squared, and then plus 2 squared pi squared h bar squared over 2m na squared plus a second 2 squared pi squared h bar squared over 2m times na squared. So basically this upper term decreases slower. So because of that, the resulting energy in part B would actually be even lower, and as a result of that, the cohesive energy, which is the difference between part A and part B, is going to be larger, and as a result of that, the resulting cohesive energy per atom that we calculate here would also be larger than what we actually got over here. So this is the result of ignoring spin, and spin is a significant enough contributor to the summation up in part B that if we didn't ignore it, this would probably be significantly larger and it would actually be in our expected range.